I wanted to do one quick example of the law of averages from the other day, just so you guys feel okay about that. So remember, the law of averages is a concept that says as n increases, as we increase our sample size, what happens to the standard error? And we looked on Tuesday, let's see. This is kind of blurry. That's better. The law of averages says that as n goes up, the standard error for the average in percent goes down, and the standard error for the sum goes up. So if we were going to do, let's do the one that we didn't do on the bottom of page 134. If I was going to do this example down here, the first step is to go ahead and say, okay, are we dealing with sums or percents? And just looking at this, I know that I'm dealing with percents because there's a bunch of percent signs. So actually any time on exam 3, if it doesn't mention percents or averages, you can assume that we're dealing with sums. So I would have to explicitly say that I want an average or show the percent signs if I wanted percents. So right away I can say, all right, this problem is about percents. So if n increases, my standard error for the percent is going to go down. Just by looking at the formula, we can see that that is definitely the case. And I have two scenarios. I want to make them equally likely. So I want the two scenarios to have the same probability. So the first one, let's see, it says 50%, give or take 6% heads in 6 tosses is about as likely as 50%, give or take how many heads in 216 tosses. So I can see that n is definitely increasing in this case. So as n goes up, how does that affect my standard error? And if I was going to label what these are, remember, these are my n, right, number of tosses, and then the 50%, that's my expected value. So expected value of the percent, anytime you have a coin, we're going to expect to get 50% heads. So that's why those two are exactly the same. With sums up here, these two numbers came from the fact that we're expected to get half heads. So it's half the number of tosses. Okay, so n is increasing by a factor of, if I do 216 over 6, I get 36. N's going up by a factor of 36. And that means my standard error for percents is going to get smaller because I divide in the formula by the square root of n. So I would take the 6 and I would divide by the square root of 36, which is 6. Right? So 6 divided by 6. My new standard error is 1%. And then now those two things, those two scenarios have the exact same probability of occurring. So we did a bunch of those questions on Tuesday, but I wanted to make sure that you guys felt okay with this. And on the exam, when you're doing the homework, if writing it out helps you, definitely do that. You can visually see as n goes up what happens to the standard error. So I think everyone's good with that after Tuesday. Let's start where we left off. So we started chapter 16, and we talked about this idea of probability histograms. And on homework, let's see, the homework that's due tonight, there's a couple examples where I give you guys probability histograms and ask you some questions about them. And a lot of times when people first see those questions, they're like, how am I supposed to know anything? But remember this, remember that the x-axis is all the possible outcomes. So if you're flipping a coin 10 times and there's a probability histogram that goes from 0 to 100, you know that those two can't match. Because if you're flipping a coin 10 times, there's only 10 possible outcomes. So the x-axis is the possible outcomes, and then the y-axis is the probability of each outcome. And we said that for any scenario involving sums, averages, or percents, there's this theorem called the central limit theorem that basically says as n increases, our probability histogram is going to look more and more like the normal curve. So that was the central limit theorem. It's very, very important in statistics because it's going to save us some time. Instead of drawing out these histograms like this, if n is big enough, we can just use the normal curve as an approximate histogram. So I didn't even draw out these two because it'll take a long time. histogram. So you guys get the idea, right? This doesn't look very normal. This looks more normal. And as n increases, the histogram's going to look even more and more normal. Okay, so the question was, how do we know what n has to be in order to say the normal curve is appropriate to use? And we said that depends on the contents of the box. If the box is nice and normal, there's nothing weird about it, you'll need less straws to look like the normal curve. So 1, 2, and 3, that's a normal box just because there's the same amount of each ticket and they're all one away from each other. 1, 2, and 9 is what we would call lopsided because we go from 1, 2, and then skip all the way to 9. And we can see for one draw, neither of these look like the normal curve. But for 2 draws, when we drew these 2 histograms, the box A, the one from box A, actually does kind of look like the normal curve already. Box B is going to need way more draws to look normal, but it eventually will. The central limit theorem says that it eventually will. So I think that was the last thing that we did. So we're basically almost done with the first part of chapter 16. These next couple questions, this is, again, that same example with box A, this nice normal box, normal, and then box B was the lopsided one. And it looks like we're looking at the probability histogram for 25 and 50 draws from each box. So looking at that, we can see that all of the histograms pretty much look normal, except for maybe, I guess this one looks kind of normal, but it has those spikes in it, because these 2 are for the lopsided box. These 2 definitely look normal. These 2 might need a few more draws, just because, again, they're from the lopsided box. And a good way to kind of think about these histograms, if your histogram looks like the normal curve, it's going to be centered around the expected value. So the value right in the middle should be the expected value, right? Z equals 0. And I don't know if you guys can see this. It's kind of, let's zoom in. It says for this one that the expected value is 50. And where that came from is, if we're looking at n equals 25 and we're looking at the sum, I can actually calculate the expected value of the sum using the formula, n times the average of the box. So for this histogram, n is 25, and then the average of this box, I can easily calculate it, is 2, right? 1 plus 2 plus 3. So 25 times 2 is where this 50 came from. So that could be helpful if you're trying to identify boxes in histograms. The expected value, when the data looks like the normal curve, the expected value is always right in the middle. And it's the same thing here. Like for this one, this is n equals 50, and 100 is right in the middle. So 100 is going to be my expected value, which is, expected value of the sum is n, which is 50, times the average of the box, which is 2. So those numbers, it makes sense that that's what should be right there. Okay, that looks good. Let's do example 5. What is up with this? It says 25 draws are made from each box with replacement. So n is the same for all of these boxes. We're drawing 25 times out of those boxes. And it says we want to match the probability histograms with the boxes. So I'm going to put, just from what I've said so far, I'm going to put this up as an iClicker question, and I want to see what you guys say. Curve. Okay, so it says which box matches the first probability histogram? So I'll give you guys a minute to think about that, and then we'll take a look. So I'm gonna put the picture back up, but it's just A is box A, B is box B, C is box C. So you guys can still, even if I'm on the document camera, you guys can still be voting with your iClickers. But what do I put, the question's asking, what do I put here? Which box goes right there? So this. Okay, I'm gonna see how many people responded. There's still a few more people that need to respond. So I'll give you guys a couple more seconds. Which one goes in the first blank? Maybe this is good. Maybe this is everyone. All right, I'm going to stop. Okay, most people said C, but then A and B, this one was kind of a tricky one. So let's look at the differences between the boxes. So most people said I should put C right here. So if I look at box A, B, and C, they all have ones and zeros, right? But box A, there's nothing weird about it. It just has a 0 and a 1. I would say this is a pretty normal box. Box B is definitely lopsided, right? Because it has way more zeros than ones. It has 9 zeros, 1, 1. And then box C is the most lopsided, right? Most lopsided, because it has 24 zeros and 1 ones. 1, 1. So we said that lopsided boxes need more draws to look like the normal curve. So if I'm drawing the same amount out of all these boxes, this box is going to look the least like the normal curve at 25 draws because it's the most lopsided. So looking at these, it looks like you guys, the majority was right. C is the most lopsided box, so that histogram is going to look the least like the normal curve. So if I had to pick, I would say this one looks the most like the normal curve. So that's going to come from box A, which is the most normal looking box. And then box B is kind of somewhere in the middle. It's lopsided, but not as lopsided as box C. So CBA, that looks good. So hopefully that helps. Lopsided boxes need more draws to look like the normal curve. So central limit theorem still holds eventually. I can even put this into our data program, 24 zeros, 1, 1. Eventually, the histogram will look like the normal curve, but we'll need more than 25 draws. Okay, so this next, let's see, what's this next one? Below are the histograms for, now we're changing our N. It says we're actually drawing 100, 400, and 900 times from a box. If I was going to draw this box, let's see, it has 99 zeros, so it has zeros, there's 99 of them, and one ticket marked 1. So it has 100 total tickets. It's definitely lopsided. Actually, this is the most lopsided one compared to at least the ones in example 5. And so lopsided boxes need more draws to look like the normal curve. So I need to match 100, 400, and 900. This one looks the most normal, right? So that should be the most draws. 900. This one looks the least normal, so that should be the least amount of draws. And then this one's close to normal, but not quite. So that follows the same logic. Lopsided draws need more lopsided boxes need more draws to look like the normal curve. All right, so any questions on that? You guys will get some more practice on the homework tonight and the homework that's due Tuesday as well. But that's kind of a review from Tuesday. The thing that I wanted to talk about today is the normal curve. So this looks like the normal curve. So what does that mean? Why does that help us at all? So the next part of chapter 16, which is part 2, hopefully should be very familiar to you guys. I'm hoping today on Halloween we don't do anything too crazy. So the normal approximation we've been doing since week 3, since the very beginning of class. And it says the normal approximation amounts to taking advantage of the central limit theorem. We can, if n is big enough and the central limit theorem kicks in, we can replace the probability histogram for the sum, average, or percent by the normal curve. And then we can use the normal curve to answer questions, kind of like we did back on exam 1. We did this a little bit on exam 2 as well. So the only difference, it's going to be the exact same thing as before, the only difference is now we're dealing with random variables, right? In exam 3, we've been talking about this idea of random variables, or variables generated by a chance process. So like rolling a die, flipping a coin, playing roulette, all of that stuff. And with random variables, we are measuring the center by the expected value and the spread by the standard error. So in my z-score formula, I just have to make that adjustment that we're dealing with random variables. So this is the z-score formula for random variables. And this looks familiar, right? Our old z-score formula was value minus average divided by SD. It's basically the same thing. We're just replacing, remember, expected values like the average. Standard error is like the SD. So that's the only difference, and everything else is the same. So this is a bit of a review. Let's do this one, 7A. The question asks, it says in 100 coin tosses, what's the chance of getting less than 45 heads? Well, okay, what I want to do is eventually mark 45 heads on the curve, shade the area to the left, use the table to calculate the area. But if I didn't know the central limit theorem, I might think, oh, do I have to draw out this probability histogram? It's going to be a huge pain. After 100 tosses, it's going to be pretty close to this. So we're going to use the normal curve. Remember, it's measured in z-scores. So if I try to mark 45 heads, the first step is I have to convert 45 to a z-score. And I guess it gives, it gives me a couple steps. I think I'm jumping the gun. If I wanted to use the z-score formula, let's just say I wanted to right away convert 45 heads to a z-score. I'm going to need the expected value and standard error, right? Values, z-score is equal to the value minus expected value over standard error. And so I know I'm dealing with sum. The question's talking about sum. So reminder of the formulas, the expected value of the sum is just n times the average of the box. And then the standard error for the sum is the square root of n times the SD of the box. And let's see, I know n is 100. So I can fill in that, but it makes sense that I should probably draw my box first. With a coin, the box, we've done this a couple times, right? For drawing our box, we want to think about one draw, so one flip. So I want to draw my box for one flip. So if I flip a coin once, there are two outcomes. So I'm going to have two tickets. And I either, let's see, what am I looking at? I'm looking at how many heads. The original question says, what's the chance of getting, is it more than? No, less than 45 heads. So for heads, if I get a head, I'm going to count it as 1. We've seen this before. And if I get a tail, I'm going to count it as 0 heads. So I'm basically simulating this coin flipping as drawing tickets out of a box. And the nice thing about this box is to find the average, I would just add up the tickets, 1 plus 0 and divide by 2. So I get 0.5. And then the SD, I could use the shortcut formula because there's two types of tickets here, 1s and 0s. Or I could think back to, I think I said this on Tuesday, maybe it was last Thursday, but if your box has half 1s, half 0s, the SD is going to be 0.5. But if you forgot that, that's okay. I could say the shortcut formula is just the absolute value of A minus B, which is 1 and 0 are the numbers on the tickets, times the square root of the fraction of 1. So there's 1 out of 2 tickets, and then times the fraction of zeros. So really common mistake that I see is people will put 0 over 2 as the fraction, but it's how many zeros are there. So there's 1 of those over 2. And that gives me 0.5. So the average and the SD are both 0.5, so I can plug those in. So let's see, my expected value is 50. Honestly, I probably didn't need a formula for that. What's the expected value if you toss a coin 100 times? The expected value of heads? I could have just said it was 50 without doing any work. Standard error isn't as intuitive, but let's see, 10 times 0.5 is 5. So for step 1, so my first step was to draw my box. And this is always going to help because it'll help us calculate our statistics. Step 2 is to find my expected value in standard error. And then my step 3 is to actually figure out what my value is in terms of a z-score. So my value was 45 heads that I am concerned about, and then my expected value was 50. My standard error was 5. So now I know where to mark 45 heads. 45 heads is right here. So this is 45 if I'm looking at the number of heads. Right at 0, that's my expected value. So that's 50, right? Expected value, we said, is always right in the middle. And I'm going to shade, the original question said, what's the probability of getting less than 45 heads? So I want to make sure to shade everything less than -1. And then this just becomes a problem like we've done before, right? I know that I can look up if I look up 1, the middle area is 68. So if I look on the table, that's one we saw a bunch of times. If I look at the z-score of 1, our table gives us the middle area between 1 and -1. And then to find this is just the tail, right? We've done this a bunch of times too. We can just take 100 minus 68 divided by 2. And that gives me 16%. So each of the tails are 16%. And then I guess if I was answering this question, my final answer would be what percent? Final answer. What is the chance of getting less than 45 heads? It is 16%. So not super high. We should get around 50 heads. Chance of getting less than 45 is 16%. Okay, we'll do a couple more. The one other thing, though, I guess, that I didn't say is the z-score. We still interpret it the same way. We said z-scores tell you how many SDs you are above or below average. Here, this z-score, we can say the same thing, but we're just going to replace average and SD with expected value and standard error. So this means, if I was going to interpret the -1, this means that getting 45 heads in 100 tosses, is 1 standard error below the expected value. So it's 1 standard error below what we're expected to get. So same interpretation, literally just replacing average and SD with expected value and standard error. Any questions on the normal curve? All right. Good. Let's do, I want to skip the next page. Let's actually go to this example. This one right here. Example 8. The next one's basically the same thing. This one's a little different. There's 3 kinds of examples I want to do today. First one is the coin. Second one is this. And then the third one's on the next page. And then we'll be good to go. So here, I guess we saw this example before, back in chapter 15. Oh yeah, we saw this box. I told you guys that the SD of this box was 3. I told that to you because you can't use the shortcut formula here, right? There's more than 2 types of tickets. So we are going to answer part B. Well, I guess part A we have to figure out first. And then part B is kind of the new thing. It says, what's the chance that the sum of the 36 straws would be greater than 120? So basically, I need to mark 120 on this curve and shade the area greater than that. Okay, so let's fill in. I'll have you guys go ahead and fill in these 2, expected value and standard error of the sum. Same formula as we did on the previous page, just a new box. So I'll put this up here. First question, you'd expect the sum to be what? So in other words, what is the expected value of the sum? So fill in, if you finish early, so fill in the first blank, vote for expected value, and then do standard error as well, because that's going to be my next question. Okay, I'm going to stop for expected value. What would we expect the sum to be? Because before we mark 120 on the curve, I don't even know what I'm expected to get. So how does 120 compare to that? So you guys said, let's check. Hopefully, yay, see, that looks good, 108. N times the average of the box, so 36 times 3. And then just because, we'll do the next one too. Give or take what? So what's the standard error? I didn't stop it, but you guys got it. That looks good. Most people are saying E, right? Square root of n, which is square root of 36, times the SD, which was 3. It is climbing. This looks great. Okay, vote for E if you haven't yet. Ooh, I've determined that it's pretty much impossible to get to 100%. I tried this in class yesterday, and there's this one person that just kept saying the wrong answer. So I'm going to stop this. Here, stop, and then that looks good. E is correct. Okay, E. So here's my work. Hopefully it was the same. There's a couple questions like this on exam 3 where they're just like, hey, find these statistics, and then as long as you know the formulas, you should get those. Easy 2 points. So now I know that 108 is right in the middle. So this is my expected value, right at 108. So 120 should have a positive z-score, right? Because it's above the expected value. So I'm going to take the value minus the expected value divided by the standard error, which in this case, my value is 120. That's what the question's asking me about. What's the chance the sum is bigger than 120 when I expect to get 108? Minus 108 divided by 18. So I get 0.7. So 120, if I want to know where to mark it on the curve, it is 0.7 standard errors above what I would expect. So 0.7 represents a sum of 120. 0 is 108. So the numbers in parentheses are in terms of sums, but the normal curve is in terms of z-scores. So that's why I converted 120 into a z-score. And I'm going to shade, it says, what's the chance the sum is greater than 120? So this time I'm actually going to shade to the right. So the question will always tell you which way to shade. Do you want greater than, less than, or in between two numbers? And for this, let's see, if I look up 0.7, it will give me the area between negative 0.7 and positive 0.7. So I will give you guys the normal curve on all exams, so you'll always have your table. 0.7 is right there. The middle area is about 52%. So I'm going to put that in the middle, but that's not my answer because my middle isn't even shaded. I want the tail, just like before. So to get the tail, I'm going to take 100 minus 52 divided by 2, which gives me 24%. So the answer to the question, what's the chance of getting a sum greater than 120? If you're drawing out of this box 36 times, it's about 24%. That seems valid. We'll do C and D really quickly as well. This is for average. We could ask about averages or percents. It says you'd expect the average to be what? Well, I know the expected value of the average is just the average of the box, which I calculated to be 3. So expected value of the average and the expected value of the percent, those ones you don't even need to think about. They're just the average and the percent. And then the standard error for the average, I do have to do a calculation. That's the SD of the box over the square root of n. So the SD was 3, n is 36. And 3 over 6, so that gives me 0.5. All right, and now the question is, what's the chance that the average is less than 4? So I'm expected to get an average of 3. So that means right in the middle of the normal curve, right at 0, my average is 3. Expected value of the average is 3. I need to figure out what 4 is, so I'm going to need to convert 4 to a z-score. So that's just value minus expected value over standard error. And my value I'm given is 4. Expected value is 3, and standard error is 0.5. Okay, everyone good? I feel like I'm not going very sloth-like, but hopefully that's okay. All right, so what does this give me? 1 over 0.52 is my z-score. So an average of 4 is out here at 2. So this is 4. It's kind of weird when the numbers make sense for z-scores. Like 3 and 4 could be z-scores. Something like 108 and 120, those are easier to tell that they're not z-scores. So here, just don't get confused. And I want to know, I'm going to shade, it says, what's the chance that the average is less than 4? So here's my z-score for 4, which is 2, and I'm going to shade everything to the left. So now my answer isn't the tail, but my final answer is going to be, okay, if I look up 2, that'll give me the middle area between -2 and +2, which is 95% if I look it up. And the answer to the question is it's definitely going to be 95 plus the left tail, right? That's all the area less than 4, all the area to the left. So because my z-score is 2, which is right here, and I want all the area to the left of that, I have to add the middle area plus this left tail, which the left tail we can find just like we always find the tail is 100 minus 95 divided by 2, which is 2.5%. So 95 plus 2.5 is 97.5%. Which kind of makes sense. If my expected value for the average is 3, the chance it would be less than 4 should be pretty high, right? Because that's everything less than 4, including 3. So that looks good for that one. The last one is basically the exact same thing, but with percentages. So it says you'd expect the percent of 2s to be, well, the expected value for the percent is just the percent of 2s. I can even put that, the percent of 2s in the box. Just like expected value, the average is just the average of the box. And here's my box, and there are half 2s. So 50%. Here's my box. It does say, though, if we just care about the 2s, it says to find the standard error for the percent of 2s. First, change the box to a 0, 1 box. So anytime we're just counting, did we get something or no, the easiest way to do that is with 1s and 0s. Because if I just draw out of this box, if I get an 8, it would be like I'm counting that as 8 2s, which doesn't really make sense. So we'll pretty much always say, you'll see in the homework, we'll say hint, draw a new box if you're just looking at a success or a failure. So a 2 or a not 2. So I think we did this before, right? Our box, we said, had 2 1s and 2 0s. So there's still 4 tickets, but basically I'm making the 2s into 1s. 2s are success. And then the 0 and the 8 are going to be 0s. So those would be counted as 0 2s. If I get a 2, I'm going to count it as 1 2. Okay, so then I can find the standard error for the percent, which is just the SD of the box over the square root of n. So it's basically the same thing as the average, but multiplied by 100 to get it in percent form. And I did draw a new box. So anytime you draw a new box, you want to make sure to use it. This box has half 1s, half 0s. So I can right away say the SD is 0.5. I could also do the shortcut formula, but that little trick, it comes up a lot. So remembering that if the box has half 1s and half 0s, there's a 50-50 split. So the SD is 0.5. And so let's see, 0.5 over n is 36 times 100 gives me 8.33% as my standard error. So from this example, the big thing is just if you're counting, did you get something or not? You don't want to like add up all the tickets or add them all up and divide by n. If you're just saying, did I get a 2 or not, you want to change it to a 0, 1 box before doing any of the calculations. And then let's see. What is the chance that the percent of 2s would be more than 60? So right in the middle, that's my expected value, which we know is 50%. So 60% is going to be something, it's going to be a positive z-score, right? My z-score is just the value minus the expected value divided by the standard error. Okay, and then let's see. So my value is 60, my expected value is 50, and my standard error is 8.33. So my z-score is 1.2. So then this, right, we'd mark 1.2. It is about right here. Here's 1.2. That represents 60%, getting 60% of whatever we're counting, which is the 2s. And then I want to find the area greater than that, right? Because it says, what's the chance that the percent of 2s is more than 60? If I have a box with half 2s, what's the probability I get more than 60% 2s? And with this one, we do the same thing. We'd look up 1.2. That would give me the middle area between positive 1.2 and negative 1.2. And then that is, if I look it up, it's about 77%. And so my answer, just like the first two that we did, the answer this time is just going to be the right-hand tail. So take note of the difference between these. Here our z-score was 2, and we wanted all the area to the left. So I did middle area plus the tail. Here my z-score was 1.2, and I just wanted the area to the right. If it said, what's the chance the percent of 2s would be less than 60, I'd have to do 77 plus the tail. So to find the tail, to find the final answer, 100 minus 77 divided by 2. 11.5%. Okay, do you guys have any questions? Everyone looks pretty good. There's one more example that I want to do. This one's actually kind of fun because I don't know, these are kind of boring to be honest. Like, who cares about sums, averages, percents? What about in the context of an actual problem? This is what I care about. Money. So, this one says if you play roulette 100 times, I like the ones that are like, you could actually think about what it means. If you play roulette 100 times, all right, that's my N, betting $1 on red each time, what's the chance you win more than $1? And then it says, remember, there are 18 black, 2 green, and 18 red in a roulette wheel. So the question is, what's the chance you win more than $1? So essentially, my goal, if I'm playing roulette 100 times, the central limit theorem kicks in. And it says my histogram for the sum. Here I'm definitely dealing with sums, right? Whenever we're dealing with money, we want to add up how much we get. And maybe I should write this down. But basically, if you guys are doing your homework, if the question doesn't mention average or percent, you can assume sum. So if the question doesn't mention average or percent, we can assume we're dealing with sum. So like this one, it doesn't really say sum, but you want to know how much you win, so you add up your money. So this one's definitely going to deal with sums. And what I would want to do is mark $1 on the curve and shade the area to the right? Shade the area, chance you win more than $1. Okay. So I can't just say $1, oh, that's a z-score of 1, because my normal curve isn't in dollars, right? It's in standard units. So I'd have to convert 1 to a z-score. Value minus expected value over standard error. But I don't have my expected value in standard error yet. I'll have to find that. So before we do this problem, I do want to ask you guys a question of what do you think about this? So example 9, we read it, right? It's roulette. What's the chance you win more than $1? If I look down here, Example 10 looks exactly the same, except now our N, it says you play roulette 900 times. N went up. What's the chance you win more than $1? So it's asking the same question. What's the chance you win more than $1? So before we actually solve this, I want to know, what do you guys think? Are the chances the same? Is one of them bigger? Is one of them smaller? So does playing 900 times versus 100 times, does that actually matter in terms of your chances of winning more than $1? So like, what should you do? If you're at a casino, should you be playing 100 times or 900 times? Or does it not matter at all? So if you had to pick right now, before we do any of this math, because sure, we can solve it with math, but let's see what our intuition says. Which scenario has a higher probability of winning more than $1? So don't worry about getting you'll get the point whatever you put. Pick whatever you think is true. And then we'll take a vote. We'll see what everyone says. So don't ask your neighbor. Don't be influenced by other people. Go with your heart. What do you think? So is it better to play 100 times, 900 times, or does it not really matter? Okay, looks like everyone has responded. Let's see. I'm going to stop. Playing roulette. Oh. You guys said B. Most people said B. Wait, what is B? Hold on. Which scenario has a higher probability of winning more than $1? Playing 900 times. Whoa, okay. Wow. Let's check. But kind of a lot of people said C. I guess A was the least common answer. So let's check. I secretly know the answer, but we're going to pretend I don't. So let's double check if this is the case. B, so let's keep that in mind. You guys think this is going to result in a higher probability. Basically, the more you play, the higher chance you have of winning more than $1. All right, good to know. So let's double check. Is our intuition correct? Because I remember before I did this problem, I had no idea. I was like, I don't know. But most people actually said one answer, so that's good. So let's find, okay, we said we have to change $1 to a z-score. So my value is $1. Let's go ahead and find my expected value in standard error. And we know for roulette, we are going to need a box. We're going to draw the box for one spin. I think we've done this before. All these examples are really similar. But for one spin of the roulette wheel, there are 38 options. So there are going to be 38 tickets. Okay, and we care. We're either going to win $1 or lose $1, right? If we bet $1 on red, the way roulette works is you either get $1 or you lose $1. And then so the winning tickets are the red. There's 18 red and 20 other tickets. So this box should look familiar. If it's a standard game of roulette, that's what our box is always going to look like. So I'm going to need the expected value of the sum and the standard error of the sum. And I knew it was sum because we're counting up how much money we earn, and no mention of average or percent. So let's see. Expected value of the sum is n times the average. So n is 100 times the average of this box. Oops, I didn't actually find it yet, but the average of the box just means I'm going to add up all the tickets and divide by 38. So I have these 18 ones, I have 20 negative ones, and then all over 38 tickets. And also another thing to point out, if you're playing a standard game of roulette, the average is always going to be negative 2 over 38. Okay, so 100 times negative 2 over 38 gives me negative 5.26. So that makes sense. With gambling games, usually you have a negative expected value. Otherwise, casinos wouldn't be in business if that wasn't the case. So we're expected, if we play 100 times, we're expected to lose $5.26. All right, so I'm plugging that in. And then I do need the standard error. So the standard error for the sum is the square root of n times the SD of the box. And with this box, let's see, I didn't give you the SD, right? No mention of SD in the problem, and that's because there's only ones and negative ones. So we could actually use the shortcut formula here. It's a little different, I guess, than some of the boxes we're used to, but it's the same deal. We have two types of tickets. So it's the absolute value of a minus b, which is 1 minus negative 1, times the square root of, and then it's the fraction of ones. So the fraction of ones, there's 18 ones out of 38 tickets, times the fraction of negative ones. So again, don't say negative 1 over 38. It's how many of those are there? So 20 over 38. Actually, if you put negative 1 over 38, your calculator will give you an error for that. So that's a good way to know if you did something wrong. But I'm going to put this into my calculator. Can we see the calculator? Sorta. So I like to do this subtraction first. 1 minus negative 1 is 2, right? Times the square root of 18 over 38 times 20 over 38. And you don't need any parentheses. I guess you can add one at the end if you really want to. But I get 0.9986. So I'm going to round this to 1. My standard deviation is about 1. 0.9986. Okay, there's so many steps to this problem, but what I'm trying to do is find the standard error. So standard error of the sum is square root of n times the SD of the box, which is 1. So 10 times 1 is 10. So I know my standard error is 10. $10. And that gives me my z-score. My z-score is 0.6. So winning $1 is 0.6 standard errors above what I'd expect. So right at 0, I'd expect negative $5.26. That was my expected value. If I wanted to mark winning $1, it's right here at 0.6. This represents winning $1. And now that I have my z-score, let's see, what do I want? What's the chance you win more than $1? So this actually isn't horrible for gambling, I guess. This looks like a nice chunk of the normal curve. So to figure this out, I would look up 0.6, right? That would give me the middle area between negative 0.6 and positive 0.6. And if I do that on my normal table, I end up getting 45% in the middle. So my final answer to the question, what's the probability you win more than $1 if you play roulette 100 times? That is going to be this shaded area. So 100 minus 45 divided by 2. Okay, so we answered part 1. Now that we did part 1, part 2 is going to be a lot easier. But if you play 100 times, this is your chance, 27.5%. Take it or leave it. Decide what you want to do from there. But what about 900 times? You guys said that the probability would go up. So not all of you, but most of you. So let's double check. Does it? Here, it's the same game. It's going to be the same box, the same average in SD, right? Because it's roulette. Same average and same SD. So I don't need to draw the box again. I can just use the one from up here. But n is changing. And if I think about my expected value formula, it's n times the average of the box. So my expected value is actually going to change, and then so is my standard error, because that's the square root of n times the SD of the box. So those are going to change, but that's okay. Let's see what we get. So n is 900 now. The average is still negative 2 over 38. So my expected value is actually negative 47.37. Okay, so my expected value is more negative, but my standard error changes too. So n is 900. My standard deviation of the box, I'm still going to, times 1. I'm still going to assume 1. So same box, same average in SD. So I'm using average negative 2 over 38, standard deviation of 1. So square root of 900 is 30 times 1 is 30. $30 is the standard error. All right, so now that I have that, I have my expected value, I have my standard error, we had to change $1 to a z-score. So I'm gonna do that again, right? I have to change, it's the same question, change $1 to a z-score using the z-score formula. So value minus expected value over standard error. And my z-score is going to change a little bit because my expected value in standard error changed a little bit. So my value is still $1, right? My value, I still want to know what's the probability, what's the chance you win more than $1. So if n changes, really the only thing that changes, that will change is my expected value, standard error, and then my z-score is based on that, so that's going to change too. So I can do 1 minus, my expected value was negative 47.37 over 30. And my z-score is a bit bigger, 1.6. Okay, right up here I got 0.6. Now my z-score is 1.6. So here's 0 right in the middle. This is negative $47.37. That's what you're expected to, that's your net profit, I guess, your net amount of money that you lost or won in 900 plays. And then winning $1 is actually right here, right at 1.6. So this is winning $1. And I want to know what's the chance of winning more than $1. And so basically I would look up, here's negative 1, here's negative 1.6. I'd look up the middle area for 1.6, and I end up getting 89%. So to find my tail, just like I did before, I do 100 minus 89 divided by 2. Which is 5.5%. Oh no, we were wrong. Guys, this is the gambler's fallacy. If you ask anybody that, they'll say, your answer was really common, so don't worry about that. But it's the gambler's fallacy. People think if they sit there like at a slot machine over and over again, they're eventually going to win, but they'll lose. They'll lose more. Sometimes you win, and then you get lucky. But yeah, the probability actually decreases, which is kind of crazy. Okay, that is it. I'm going to put up, one of my colleagues in the College of Education asked me if I could ask you guys if you want to do a survey. So I'm going to put up a QR code to a survey. You do not have to do it, but if you're interested in helping with research, today, so much stuff about research, I'm going to put it up. Have a great Halloween. Happy Halloween. I'll see you guys next week.